Good day. For those of you who do not know us, we're the instructional staff for ECE 150. Professors Hiran Patel and Werner Dietl and Douglas Harder. In this topic, we're going to look at authoring functions, or how to write a function body. In this lesson, we will describe the idea of reusing code. Specifically, we're going to look at the issues with what happens if you cut and paste your code in multiple locations in your programs. We will describe how to author a function body in C++. We will look at how parameters can be used in that function body. We will look at various implementations of functions, including a simple sine function, an absolute value function, a function that returns the maximum of two parameters, a function that evaluates a cubic polynomial at a point, and a function that finds the maximum of three parameters. We will then look at how we can use function calls within a function and see numerous other examples with various discussions. Okay, to this point, we have described the concept of a function declaration, and we've seen int main, but we've also seen declarations for functions such as the cosine and power function. The function declaration simply tells you the number of arguments that are required to call that function and their types, as well as to the left of the identifier giving the name of the function, the type that is returned. Now, we have so far engaged in using one function definition. Every time we wrote a program, we had to implement the function main, and of course we returned 0. Someone else implemented the cosine and power functions in the standard C math library. However, in this topic, we're going to see how we can write functions that you can call explicitly from within your programs. Suppose, for example, we do not have access to the C math library. However, we have a program that still requires you to calculate the absolute value of a local variable. For example, you may be reading data from a noisy sensor, and you'd like to determine what the error is. This would require you to calculate the absolute value of the expected value versus the actual value. So in this case, we're asking the user to enter a real value x, and then we're calculating the absolute value of x minus pi. That is the error between x and the closest approximation of pi. As you can see, this is not very clear what the code intends. There are no comments, and it's 4 lines of code to calculate a reasonably straightforward operation. With comments, it's going to be even longer. We may have to do this again and again and again. However, every single time you author any piece of code, there's always the possibility you may introduce an error or a bug. Here's another example. Suppose you are authoring a piece of code that requires you to repeatedly calculate the maximum of two values. Basically, you may have 2 weightings that give you the best possible strategy or the best possible path to follow, and you'd like to figure out which is the optimal path. So this piece of code asks the user for 2 numbers x and y. It then declares a local variable z, which is assigned the value of x. We're going to assume x is the maximum. However, if y is greater than z, we will then assign z the value of y. This will consequently give z the value that's equal to the maximum of x and y. Once again, this is 4 lines of code to calculate a reasonably straightforward expression. Now, One thing you should note in both pieces of code that we just saw, it's not entirely or immediately obvious what the code is doing. You actually have to examine the code and deduce what it is performing, either that or you have to include and then read comments. Also, you will have to perform these operations every time you want to perform either calculating the absolute value or the maximum of two numbers. What is the likelihood that if you do this over and over again, you are never going to introduce a mistake or some sort of bug? Probably not very likely. And as we get to more and more difficult problems that we are trying to solve, and if we are solving those problems repeatedly, we will find that it's very common that bugs get introduced. So if you find yourself performing the same operation in your program more than once, you are essentially cutting and pasting your code throughout your program. Here are some questions you should ask yourself. What happens if you determine, oh, the best way to perform this calculation is slightly different from what I've done? So you may go there and update one of your versions of the code, but you forget everywhere else where you've included that same code. Alternatively, what happens if in your lines of code you actually have a bug? You copied that bug everywhere else, but then when you're testing, you find one of those bugs. How do you know, or how do you remember everywhere else you have to go to fix that bug? Again, this becomes a maintenance nightmare. So what we're going to now look at is how can we use functions to solve this problem. A function in C++ is a means of authoring a piece of code to perform one straightforward operation once. It will take some arguments and it will perform some operation and give a return value based on those arguments. Once that function is tested, you and anyone else can use it again and again without ever having to worry about it being correct or not. It's already been tested. Other people are using it. If someone finds a bug, that one function can be corrected, and then everyone can make use of that correction. Also, everywhere where you have called that function will benefit from that correction. We've already seen numerous functions implemented in the C math library, and you don't care how they're implemented, you just assume that they are implemented correctly. The nice thing is, once you start authoring functions, people won't care how your functions are implemented so long as your functions have been tested and thoroughly documented. Now here's an example of a function declaration for my sine function. Like the sine function, it takes a double and it returns a double. The function definition has a body that is executed when the function is called. So let's look at the different components of the function definition. First of all, we have the function identifier or function name. Here we see the parameter x and its type, or the parameter type. The parameter, any argument to this function, must be of type double. Here we see the return type, so this function must return a real number or a double, a floating point number. Anything between the two braces is the function body. Now we've already seen the function body numerous times before in the main function. In this case, this function body has only two statements. This is a local variable. Just like a local variable to a to the main function, the local variable result is local to this function. You cannot access the value of result anywhere else other than within its scope within this function. Now, this local variable is being initialized with an algebraic expression. It's actually the first three terms of the Taylor series for sine of x. And we're going to see that it's actually not that bad in some circumstances. Finally, in this function, we have the returned value. So in a function, when you see the keyword return, whatever immediately follows it up until and including this up until the semicolon, the value that works out to, or whatever it evaluates to, is the value that is returned by this function. We can now use the mysine function in this program, where we would insert the function definition of mysine at the bottom of this page. So we have two function declarations, that of main and mysine, and two function definitions. Inside the function main, we call mysine with the argument 0.4. So what happens here is, here's the mysine function. The parameter x is initialized with the value 0.4. So now x is an identifier local to this function, and its initial value is, in this case, 0.4. Anytime x is referred to, its value is 0.4. So in the first statement, the local variable result is initialized with the calculation x minus x cubed over 6 plus x to the 5 over 120, where x is taking on the value 0.4. So whatever this evaluates to, result is initialized with that calculation. Next, mysine returns that result, and so whatever that evaluated to is returned, and that is what will be printed to the console. When this program is executed, we see that mysine and the standard sine function return values that are almost identical, and we have an approximation that is correct to 5 significant digits. So in your calculus course, you will learn why this is the case. Let's look at another example. Here's the declaration of the absolute value function. I'm going to be authoring this, so I will call this my abs. That is my absolute value function, not my abdominal muscles. So here is the function definition. In this function, we will have a local variable result. We will do something to calculate the absolute value of x and assign that to the local variable result, and then we will return that value. Result is local to this function body. That is, the scope of result is the function myAbs. You cannot access that local variable anywhere else other than inside this function. So for this function myAbs, the identifier x is called a parameter of the function. For different arguments, the output of the function may be different. So essentially, this identifier x parameterizes the function. The value that the function returns will change or may change depending on the value of the argument that is passed. The scope of any parameter is restricted to the function body. So it's essentially like a local variable, the scope of which is the entire function body. X can be accessed and modified within the function body at any point. The initialized value of the parameter is the value of the argument that is passed in the corresponding function call. Now, what's the expected return value for the absolute value function? If the parameter x is greater than or equal to 0, the function should return x. If the parameter is less than 0, we should be returning negative x. So here's one implementation of the function body for the myAbs function. I have a local variable, result. If x is greater than or equal to 0, result is assigned the value of x. If the condition is false, therefore x must be less than 0, in which case result is assigned the value of negative x. Whatever value result has right now, that value is returned from this function. We can now use this myAbs function inside our program. So first, myAbs is called with the argument negative 0.3. Consequently, the myAbs function is executed where the parameter x is initialized with the value negative 0.3. This will, of course, ultimately result in result having the value 0.3, which is then returned, and 0.3 is printed to the screen. In this case, we call the function again. The argument is now 0.1. So in the function myAbs, the parameter x is initialized with the value 0.1. At the end of the execution of the function, result will still have the value 0.1, which will then be returned. And so the second cout statement will print 0.1 to the screen, as expected. And finally, once again, here the argument negative 15.9 is passed to the function. The parameter x is initialized with the value negative 15.9, and myAbs will return 15.9, which will be printed to the screen. Now, suppose you have the following cubic spline. A cubic spline is a cubic polynomial that has specific restrictions. This one in particular satisfies the following conditions. When x equals 0, the value of this cubic is 0. When x equals 0, the slope at that point is 1. When x is equal to pi over 2, the value of this cubic is 1, and the derivative at pi over 2 is 0. As you can see, at least on the interval from 1 to pi over 2, this cubic spline actually does look a lot like the sine function, which has those same properties. Let's implement this polynomial as a function in C++. That is, we want to implement a function that returns the expression we see there. So, of course, we will need m underscore pi because those are constants that are required. All right, so we include the CMath library. We have the function declaration that spline takes x as an argument, and it's of type double, and it returns a double. Now let's go down and look at the function. This function has only a single statement, return followed by an algebraic expression. If you take a look at this algebraic expression, you will see that it does indeed contain all the particulars of this cubic spline. Here we see 4 times x squared over pi squared. This is then multiplied by x minus 4 over pi times x minus pi plus 3, and then added to this result is x. Here, the right-hand side of the return statement is an algebraic expression. Whatever that algebraic expression evaluates to, that is the value that will be returned by this function when it is called with a specific argument. Inside main, we can now use this function. In this case, what we'd like to do is break the interval from 0 to pi over 2 into 11 equally spaced points, which means that this breaks the interval into 10 equally sized subintervals, each of width pi over 20. In order to achieve this, we have a for loop where the loop variable starts with the value k, and it takes on successively larger values of k, going from 0 up until and including the value 10. We will then print pi over 2 times 0.1 times k. 0.1 is a float, and so k will be converted from an int, from its integer value, to a floating point value. That result is then multiplied by the constant pi over 2. Notice here that same calculation is the argument to the call to the spline function. So whatever pi over 2 times 0.1 times k evaluates to, that value is assigned to the parameter x when the spline function is called. Similarly, for comparison, we're also going to print the value of the sine function at each of these 11 points. So if we now execute this function, the output, okay, you can see how I was using a comma and a tab character in order to line up the columns. It didn't work in the first and last rows, but everywhere else it seemed to do okay. Notice that on the left hand, in the first column, or the left-hand column, we have the 11 values going equally spaced between 0 and pi over 2. In the second column, we have the values of the spline function, and in the third column, we have the values of the sine function. Notice that the spline is usually either 2 significant digits or almost 2 significant digits when compared to the actual value of the sine function. This is useful in engineering because in engineering, approximations are something that are used very commonly, especially in computer programs. Here is a different use of the return statement. The return statement does not necessarily have to be the last statement in a function. Here, for example, we have an implementation of the max function. So we see the function declaration and a function definition. The max function has 2 parameters, x and y. When max is called with 2 arguments, the parameter x is initialized with the first argument and the parameter y is initialized with the second argument. Now, inside the function body for max, if x is greater than or equal to y, then we execute the statement return x. This immediately returns from the function to whichever function called it, and the returned value is the value that is assigned to the parameter x. If x is not greater than or equal to y, that means x is less than y, and so therefore the maximum of the two is y, and so in the alternative body we have the statement return y. So once again, at this point, the value y is returned to whichever point this function was called. Here we have an example of a function call inside an argument to a function call. So in this main function, we query the user for a real number, and that whatever the user enters is assigned to the local variable z. Now, inside this statement, the first thing that executes is the call to myAbs with the argument z. Let us assume the user entered the value -0.1. In this case, myAbs is past the value -0.1. The parameter x is assigned -0.1, and after computing, it returns 0.1. Having calculated 0.1, we now subtract 1 from that value, giving a result of -0.9. 0.1 minus 1 is -0.9. -0.9 becomes the argument for the next call to myAbs, in which case myAbs will then be called and return the value 0.9, as that is the absolute value of -0.9. That is the value that would be printed to the screen. We can use the absolute value function inside another function. Here I'm introducing a new function w. It takes a single argument and it returns a float. Now, what it calculates is the absolute value of the difference of the absolute value of 3x minus 3. So, for example, if w was called with the argument -0.1, then first we would calculate 3 times -0.1, which is -0.3, and that would become the argument to myAbs. MyAbs would perform the calculation and return positive 0.3. We would then calculate 0.3 minus 3, which is -2.7. -2.7 would become the argument to myAbs, which would then evaluate to positive 2.7. This is the value that would be returned from w. Here we are using the function w inside a program. In the program, I have a single for loop which iterates from the loop variable k going from -20 to 20 inclusive by steps of 1. It then prints out 0.1 times k and evaluates the function w at 0.1 times k. So essentially, it evaluates the function w at -2, -1.9, -1.8, and so on, all the way up to 2. Rather than printing this out, this forms the following very familiar shape. If you have been to Waterloo, you would of course recognize this, for as you enter the campus, you see the sign out front. Now, as the requirements of a function become more complex, so do the implementations. In this case, we have a function max that takes not 2 arguments but 3 and returns the maximum of the 3. So in this case, we have a cascading conditional statement which checks each of the 3 cases to determine which of the entries is indeed the largest. There are times, however, where you can use previously defined functions. we have already defined one max function that takes 2 arguments, and consequently, in implementing a max function that takes 3 arguments, we could just ask for the maximum of the first 2, and whatever that is, we will return the maximum of that and z, the third argument. Now, this is an interesting case of using other functions in order to simplify the task. Some of you may argue this may be ever so slightly slower than the previous implementation we saw on the last slide. True. However, this is very clear as to what it is doing. Also, if the max function works with 2 arguments, you're guaranteed the max function works for 3 arguments, and there's no possibility that you may have gotten 1 or 2 of the inequalities or conditions wrong. As far as the compiler is concerned, we now have 2 different max functions, one that takes 2 arguments, one that takes 3. The compiler is intelligent enough so that if you call max with 2 arguments, then it will call that max function that has 2 parameters. If you call max with 3 arguments, then it will call this max function instead. The compiler can do that. Now, one important thing to remember is we have already authored a number of different programs in the main function. Anything that you did in the main function can also be part of any other function. However, other functions specifically take parameters and return a value based on the description of that function. So, for example, n factorial is the product of n times n minus 1 times n minus 2 all the way down to 1, which is of course equal to 1 times 2 times 3 all the way up to n. So here we have a function to calculate n factorial. N is a parameter of this function, and therefore we have a local variable result which we initialize with the value 1. We then have a for loop where the loop variable takes on all values from 1 up until and including n. Each time we multiply the result by the loop variable. At the end of this for loop, the local variable result has the value equal to n factorial, and therefore we return that result. Now, one thing that's very important to remember, there are many equally valid ways of writing the same function. You don't have to author it exactly the way I might. For example, here's one implementation of the absolute value function. We have a conditional statement, and the condition is if x is greater than or equal to 0, what we do is we return the value of x. Otherwise, we return the value of negative x. Alternatively, you could declare a local variable result. Then, if x is greater than or equal to 0, you assign to result the value of x. Otherwise, you assign to result the value of negative x, and then you return the result. Here's another possibility. You declare a local variable result and you initialize it with the value of the parameter x. Then you check. If result is less than 0, you assign to result its negation, and then you return whatever the value of result is. Here's an interesting fourth variation. Remember that the parameter x is just a variable, the scope of which is the entire function and restricted to that function. So if it is a variable, we can assign to it. So let's check. If the parameter x is less than 0, then we assign to x the value of negative x. We then simply return x. Now, this one might be a little bit less intuitive, but all four of these are equally valid means of implementing the same function. Here, for example, is one way of writing the max function. If x is greater than or equal to y, we return x. Otherwise, we return the value of y. Alternatively, you could have a local variable result which is initialized with the value of the parameter x. Then you check. If result is less than y, then you update the result by assigning it the value of y. You then return result. Alternatively, again, we could just check. If x is less than y, then we assign x the value of y and we just return the value of x. This one may be less intuitive, but again, x and y are simply variables that have a scope restricted to the function body. And in that case, we can assign to these variables, just like we can assign to local variables. In a similar fashion, here are three ways of writing the max function with three parameters. Now here's one implementation of the max function on three parameters, which is actually the most efficient. That is, this particular implementation will result in compiled code that has the least number of instructions required to be executed in order to get the correct answer. Now, the difference is essentially trivial. However, you may be interested to try to work out why this actually does return the maximum of the three parameters, and you may try to guess why it is also the most efficient. You can compare this with the previous ones. What do you have to do to actually get to the return value? Now, when you take your course on digital computers and start looking at machine instructions, you will get a better idea as to why this is a slightly more efficient implementation. Now let's write a function that solves a specific problem. We're going to write a function that returns the root of the linear polynomial ax plus b. Now, if ax plus b is equal to 0, then ax must equal negative b, and therefore x must equal negative b over a. Note that we don't really care about the variable. Negative b over a is also the root of a y plus b and a xi plus b. Consequently, to find the root of this polynomial, all we really need are the values of the two coefficients a and b. Thus, a reasonable function declaration is as follows. We will name this function linear root. That tells us what the function does. It finds a linear root. The two parameters are a and b, and both of them are floating point numbers. It will return a double, as that will be the value of that root. Now, if the user calls this function and switches the order of the arguments, the user is going to get the wrong answer. And so it's important in the comments to let the user know exactly what the function and what the function does, and the purpose of the individual arguments. Here's our function implementation, and as you may have guessed, it's reasonably straightforward. However, we're going to add some comments. First, we'll give the name of the function, linear root. We will specify what each of the parameters means. In this case, a is the coefficient of x, and b is the constant coefficient. Then we'll give a description of what the function does. find a root of the linear polynomial ax equals b, and in the comments I also add a derivation of how we got that answer. Consequently, the actual implementation of the function is quite straightforward. We just return negative b divided by a, again assuming that a is not equal to 0. Following this topic, you now understand how to author a function body so that it takes the values of the parameters and returns an appropriate result. You know how to use and modify parameters inside a function body just as if they were local variables, only rather than initializing the parameters themselves are initialized by the arguments that are passed to the function call. You understand that there are multiple ways of implementing a function that satisfies the same requirements, and we took a look at a number of different functions in this topic. You have an idea of how to start authoring a function based on the requirements for that function in question. You also know that you can call one function from within another function. And you should have an idea that there are sometimes easier ways of implementing a function that performs the same calculation. Therefore, you should be able to deduce that more difficult implementations are not necessarily better. You want something that returns the appropriate result for what's expected of that function call. Now, you're going to look at numerous examples, and throughout this course, you're going to have to deal with authoring numerous different functions. So this is just the start of the rest of your life. Here's the references, acknowledgements, a colophon, and a disclaimer. Cheers!